Hello my friends. We were trying to study about Schur's theorem, right? So Schur's theorem is a combinatorial theorem which talks about colorings on integers. So Isaac Schur, a mathematician, proved this theorem using pigeonhole principle that we have already discussed in previous lectures. So it tells you if positive integers are colored using finitely many colors, then there is a monochromatic solution to the equation x plus y equal to az. So I have illustrated this using a particular coloring. For example, suppose you look at this color, then you can see that one is colored violet, 2 is red, and 3 is something and a pink, and 4 is again violet, 5 is violet, like that. So it colored, assume that it colored some way, right? And you can see that 1 plus 4 equal to 5, and also their colors are same, 1, 4, 5 all have same color. So this particular coloring of integers gives rise to this a monochromatic solution, but we don't know for every coloring it is possible. So Schur has proved it. Okay, so today we are going to see two versions of this particular theorem. One we have discussed was infinitary version of Schur's theorem. That means you may get solutions anywhere in integers. We are not telling any boundaries for that, right? But the finitary version tells you that suppose you have a particular number r and you color the integers using these r many colors, right? For example, suppose you want to color the integers by just 4 colors, right? Now what is finitary version tells you that there exists a natural number which exactly depends upon the number 4. Here I am telling for integer r there is a number nr, such that any map phi from 1 to nr to these r colors will give you a monochromatic solution, right? So basically this is an exhibition of a particular bound, such that you don't have to go for infinitely many. You will definitely get a number where any map from nr to r. So I may denote this set is box n of r, that is 1 to nr, and this is simply so any map from nr to r, this is a coloring. Any coloring from nr to r will produce a monochromatic solution. So you will be able to get such a natural number, right? So these are two versions, and in this lecture I will establish the equivalence between these two. That means finitary implies infinitary, and infinitary exactly implies finitary, right? Yes. So we can just start from the easy way, that is, assume finitary version, then we will get the infinitary version. So we assume finitary version. So what is, we assume that for each r there is a number depends on R such that any map from NR to R colors will produce a monochromatic solution. So this is very simple to prove the infinitary version. So I take a coloring phi from N to R, and I have to show that this actually produces a monochromatic solution, right? But I know that by finitary version there is an NR such that any map from NR to R gives rise to a monochromatic solution to x plus y equal to z, right? So what I will do is I will find a restriction of phi to NR, right? So if I restrict phi to NR, then I will get a map from box NR to box R, right? But whatever the map, so this is a map from box NR to R, so that will produce a monochromatic solution. So since the restriction produces a monochromatic solution, surely the full phi will produce the monochromatic solution. So that is a simple thing. You can think about it if you have any doubts. Now we assume the infinitary version. Here is the trick. We assume infinitary version. That means for each map N to R, box R as a monochromatic solution, then I have to exhibit a natural number which depends on R such that any map from box NR to R gives you the solution. It's not that obvious, right? Yeah. So we assume the infinitary version. Suppose the finitary version is false. We are going for a contradiction, right? Suppose finitary version is false. So then we have to know that what do you mean by a finitary versions. So finitary version tells you for each R there is a natural number, such that any map from N to R give rise to a solution, right? Then if you go for a negation, you have to fix an R such that for each N there is a map which avoids monochromatic solution, right? So for each N there is a map phi N which is from N to R which avoids monochromatic solution. So we get actually a sequence of functions, which are where the codomain is same but the domain are changing, right? Because phi 1 is from 1 to R which avoids a monochromatic solution, phi 2 from 2 to the box R which avoids a monochromatic solution, so on. So phi 1, phi 2, phi 3 be sequence of maps which maps box 1 to box R, box 2 to box R, box 3 to box R. What is a property respectively which avoids monochromatic solution to the equation x plus y equal to z. Alright, so we got a sequence of maps which actually avoids monochromatic solutions. Now I consider as an infinite sequence made up of these R colors like this. I put my value 1 in phi 1, of course 1 is in the domain, and phi 2 of 1, and so on. So this is an infinite sequence made up of R colors. Then by pigeonhole principle there is one color, right? So these fellows are now these all these values are maps. All these values are put into only R baskets, right? We can't give colors to only R colors. So since this is an infinite sequence, there will be one color which one basket, I mean one hole, contains infinitely many colors. Otherwise, what happens? Every basket has finite colors, the sequence will be finite. That is not possible, right? So there is a color, let's call R1, right? R1 such that, and a subsequence of natural numbers, of course, a subsequence of that particular, I mean sequence of functions anyway, such that phi of an1 of 1 equal to R. What is the meaning of this? The thing is, I told you this sequence goes to a basket of color, one particular basket, a color basket, right? So that means a sequence of natural numbers, suppose we call an1, and the suffix will go to this phi an1 of 1 is equal to R1. That means an1 is a subsequence, not a particular element. an1 is a subsequence. This n1 is changes, we don't know what is that n1 and all, right? Because it is a subsequence of an, right? So n1 takes some values greater than or equal to 1, we don't know that. But that subsequence, along the subsequence, that particular phi maps 1 to R1, right? So along the sequence an1, there is a lot of maps, right, along the sequence. All such maps, all such function maps 1 to R1. That is the meaning. Now we take the corresponding an1. We consider the sequence phi an1. So what is the, now we consider the sequence subsequence phi an1 of phi n. Phi n is a map. Phi n is a map which avoids monochromatic solution. So this is phi n is a sequence. We already seen that, and we got a subsequence of phi n, right? What's the property? One maps to same color, right, in each of the elements in a subsequence. Fine. Okay, so phi n1 is a subsequence of phi n in which one maps to R1 in each map within the subsequence. Now what we are going to do is, we got this particular subsequence, right? Now we put a value 2 into that. Then again that going to be an infinite sequence, right? Phi an1 of 2 is again an infinite sequence. Again applying pigeonhole principle, infinitary version, then you got a subsequence of subsequence an2 of an1 such that phi an2 is equal to 2. I mean phi an2 of 2 will be some color R2, which you are getting from pigeonhole principle, and also phi n2 1 is R1, because you already stabilized the image of 1, and now you are choosing functions from the same along the subsequence. So 1 is mapped to same color, now 2 is mapped to another same color in each element within the subsequence. So now you continue this process. What happens is, for each k you will get a subsequence ank of n, which phi ank of I equal to Ri 1 less than I less than or equal to k. What is the meaning of that? For each k means natural numbers, you will get a stabilized subsequence which stabilizes the what do you mean by stabilization? 1 maps to a color, 2 maps to a color, 3 maps to color. This is in every element within the subsequence. Up to k you will get. For each k you can stabilize up to k such a subsequence is possible. Okay, right. Now define a function from n to box R, right? Something like this. Phi of n is equal to phi of nk of n for large enough k. So this is a thing you need to understand a little bit. I mean, I told you for each n or for each k, whatever, there is a subsequence where and each element of the subsequence, right, we get phi a n k, right? So each element there is a map. So in those maps, one goes to a particular color in all maps, 2 goes to particular color in all maps, and finally n goes to particular for all maps, right? So you are taking the color of n in such a stabilized sequence, right? So for a large enough k means if you change the k from greater than or equal to n, nothing will happen, because so basically it starts from n. The nth stage you are stabilizing up to n. Then the n plus 1th stage you are stabilizing up to n already. Then you stabilize as n plus 1. So in n plus 1 case also the color will not change, because it's a map and the color of map will not change. That means it's a well defined, right? So it's a well defined function. Okay, right. Now, so what is the meaning? So this means nth stage you get a subsequence where all maps the subsequence 1 up to n2, r1, r2, rn respectively. Now any stage after this there is no change of the image 1 to n, right? There will not change. If the next stabilizer sequence will always stabilize the image of 1 to n after n. Okay, so there is no problem. So this is itself a color, because this is a map from ANK box ANK to R, right? This is a map. So no worry about that. So now suppose our phi has a monochromatic solution. What happens is, and before that I want to tell you, suppose you understand this, we already discussed it in some way. Suppose y equal to the color of x in the xth stabilizing stage, getting the sequence, okay, and y bar is nothing but zth stabilizing stage, and suppose x greater than or equal to z, then what you can say? Since ANZ is ANX is a subsequence of ANZ, you are already stabilized Z. Then you are going for stabilization of x. So what you can say? Phi ANX of Z is also y bar, right? So the next stage of getting the subsequence will not change the color. That means if you have a bigger fellow, you can change this suffix, right? That is what we can say, right? Because ANX is a subsequence of ANZ. Now suppose phi has a monochromatic solution, right? Suppose phi has a monochromatic solution. Then what happens? Phi of x equal to phi of y equal to phi of z. That means phi of ANX x, phi of ANY y equal to phi of ANZ z. Right? Because the x is stabilizing state. Now without loss of generality, I assume that x greater than or equal to y greater than or equal to z. So I got z stabilizing stage, so up to z is stabilized. Then I go for yth stabilizing stage, then z is stabilized, z goes to same color, y goes same color, all of the subsequence. And after that I am getting ANX, which is again the refined form of maps, where y z already goes to a particular color in all of the elements. Now x is also goes. So I can replace this ny's by just anx, because in the whole case the maps are, the colors won't change if you map the suffix. That means phi of anx x equal to phi of anx, y equal to phi of anx. That means this is looks like our old map. What do you mean by phi ANX? This is a natural number, right? That means phi ANX is a map from ANX to box R. So this has a monochromatic solution. That's what it tells. But that is not possible, because we assumed the negation of the finitary statement. right? So these maps are avoids monochromatic solution. So this map actually avoids a monochromatic solution, but we got this has a monochromatic solution, so that's false. That means phi has no monochromatic solution. But that is a contradiction to the infinitary statement. Infinitary statement says any phi from n to r gets a monochromatic solution. So we got a contradiction, series of contradiction, because we assumed finitary statement is false. That means finitary statement is true. Right? So this is a equivalence between finite and infinitary. So you go once again through the lecture, and if you have any doubts, you can mail me, and you can ask in the comment box. Thank you.